In this video, I'm going to talk about simple harmonic motion, which is the repetitive movement back and forth through an equilibrium of an object. An equilibrium is just the center point. So this is best explained with a pendulum. I have a pendulum here when it's furthest up, and then this is when it goes through the center, so that's equilibrium, and this is when it goes up again. So a pendulum would swing from a point over there down to a point over here and go up again. So makes a curve. That pendulum would go back and forth. So I have a pendulum here in this position here. So in this position, the velocity of the bob at the end of the pendulum is 0. So the velocity is equal to 0, because if you think about it, it's not moving at all. It's staying in one place. And it's at this point at which acceleration is maximum. So if you think about it, gravity is acting at its best at this point because it's trying to push it the hardest over this side. So it's accelerating the most at this point. At this point over here, you're in equilibrium. So over here, I'll just write here. That's equilibrium. And at this point, the velocity is maximum. Because if you think about it, the bob will be going the fastest. So it'd be stopped over here because it goes up, it stops. It goes really fast when it goes down to here. And then it slows down as it gets to here again, and it stops. So at this point, which is here, the velocity is maximum and the acceleration is 0. So it's not speeding up or slowing down at this point. And this point over here is furthest to the right. It's the same as this one. So at this point, velocity is equal to 0 and the acceleration is max. Okay, so this was simple harmonic motion on a pendulum. Now I'm going to go ahead and talk about what simple harmonic motion is like on a spring. So, for example, if you have a compressed spring, like here, the spring's compressed. When you let go of the spring is going to open up and go out to some distance. But then the spring would contract again, so it would go back to this position. This is also simple harmonic motion because if you think about it, if I draw it on a line, let's assume this is a compressed spring over here. When the spring is opening out, at this point the spring is stopped, but when it goes out to here in the middle, this could be our equilibrium point. At this point, like above, at the equilibrium, acceleration is 0 and velocity is maximum. So at this equilibrium point, the velocity is maximum and acceleration is 0. And when you come out to here again, the acceleration would be maximum, but the velocity would be 0, because if you think about it, the spring would stretch out all the way and then it would stop. But then it would be pulling itself back. And when it gets to here again, it'll get fast. The fastest it can be, and then it go back to being a spring. So simple harmonic motion can be represented on a line like this, where the middle is equilibrium, and these are the two ends. So we'll call this A and B, and this is the equilibrium point. So now I'm going to talk about some of the equations that you'd need in the Leaving Cert Applied Maths exam for simple harmonic motion questions, which often appear as question 6 on the paper. So the first equation is A is equal to minus omega squared x. This equation is the defining equation for SHM. This is the equation that you'd always need to prove to show that something is going in simple harmonic motion. In this, A is acceleration, omega is the angular velocity, and x is the distance away from the center. So I'll go back to the line. So we have the equilibrium point. Let's say you have another point over here, and let's call it A. The distance between here and here would be x. That's the distance between here and here. So x is measured in meters. Omega is measured in radians per second. And we'll move on to the second equation. So the second equation that you need is v squared is equal to omega squared by a squared minus x squared. Okay, so v is the velocity at a given time. Omega, once again, measured in radians per second, is the angular velocity. A is the amplitude, which I'll explain in a second. And x, once again, is the position or the distance away from equilibrium. So v, of course, is measured in meters per second. And A is amplitude. So amplitude is, I'll label this B here. And this is equilibrium. This is the end of the spring, where if you recall, when the pendulum went to the end, it stopped at one point and the acceleration was maximum while the velocity was 0. That is the point of amplitude. So the distance from B, from equilibrium, would be A, which is amplitude. Amplitude is also measured in meters, because amplitude is the distance from equilibrium to B. So now I'll move on to the third equation, which is T is equal to 2 pi over omega. T, as you may know from circular motion, is the periodic time. It's measured in seconds. So you can say seconds per oscillation. So how long it takes to make one oscillation. So one oscillation would be, let's say you start at B, you would go all the way to the end over here to a point. Let's say the point is point C. So if there's a point C over here, the distance from going from B all the way up to C and coming back, all of this would be 4 amplitudes, which is one period denoted by T. So 4 amplitudes is equal to 1 period. So 1, 2, 3, 4, 4 amplitudes. Now the fourth equation I'm going to give you is F is equal to 1 over T. So this is the frequency. F is the frequency, which is measured in the number of oscillations. So it's not a proper unit, but I call it OSCC. And some of you may also know that you can also call the unit hertz. So it's oscillations per second. So the period was the number of seconds in one oscillation. This is the inverse of that. It's the number of oscillations per second. Now, for these two, you need to learn these two off by heart because they're not in the tables, so you need to learn these off. So now I'm going to talk about the fifth equation. The fifth equation is Vmax, so the maximum velocity, is equal to omega A. So if you think back to when I drew the line, and there were 3 points, and I explained this with the pendulum as well. When the pendulum was at the end, or when the spring is at the ends, acceleration is max and velocity is equal to 0. At this point, velocity is equal to max and acceleration is equal to 0. And this point, A is max again and velocity is equal to 0 again, because this point and this point are identical in terms of what happens. So we're looking at this point because we're looking at the maximum velocity. When does the maximum velocity occur? It occurs when the acceleration is equal to 0. So we can, you don't need to be able to derive this, by the way, but it's just good to know. So you can use v squared is equal to omega squared by a squared minus x squared. If you sub in x is equal to 0, because if you recall, x is the displacement from the equilibrium point. So if you sub in x is equal to 0, you get v squared is equal to omega squared bracket a squared minus 0. So it's then you can square root both sides and you get v is equal to omega a, which is what we have here. So v max, maximum velocity, is equal to omega a. Okay, and it would be worth your while kind of understanding this derivation, because this equation, like these two, isn't in the tables, so you would have to learn this one. Okay, so now I'm going to go on to the 6th equation. This one is A max, the maximum acceleration, is equal to omega squared A. Now, once again, this one isn't in the tables, so I'm going to derive it for you to help you remember where it comes from. So if you look back at the equation where I had A is equal to minus omega squared x, you're going to start off with this, and to get the maximum acceleration, we'll look back at this diagram. Maximum acceleration occurs when the particle is at the amplitude. So when in terms of the pendulum, the bob was at the very end. So that's the point when velocity is 0 and acceleration is maximum. But what is this point? This is the amplitude. So that's the equilibrium over here. That's the amplitude. So this distance over here is A. So you have A over here, from here to here. So to get A max, we're going to sub in A instead of X, because the distance from the center, or the equilibrium, is A at the point of maximum acceleration. So A max is equal to minus omega squared A. Now, there's a minus there, but you just ignore the minus, because the minus is there for the direction. It just denotes direction, and we're only speaking about the magnitude here. So you say A max is equal to omega squared A. Okay, so now I'll talk about the 7th equation, which is omega is equal to V over R. Now, this comes from the fact that theta is equal to L over R. You should know this because of maths. This is a basic definition in maths, and it's also in your tables. So to draw it out, theta is the angle subtended in a circle. So if you have a circle, theta is the angle subtended, and L is this length over here. This is L, and R is the radius, so I'll do that in orange. So this is the radius over here. So by definition, theta in radians, not degrees, so you have to use radians. Theta in radians is equal to L, which is the arc subtended, over the radius. You divide both sides by T, so you get theta over T is equal to L over RT. Theta over T, so that's radians, that's seconds, radian per second. So that is omega. Omega is theta over T, because radians per second, that's the unit. I said that over here as well. Radian per second, that's the unit for omega. So omega is equal to, now L over T. L is a length, so it's measured in meters. T is time, so it's measured in seconds. So L over T is meters per second, so it's velocity. Velocity is L over T, or meters per second. So V over R. So there you have it. Omega is equal to V over R. Now, for the next equation, equation number 8, you have T is equal to 2 pi R over V. Now, this is based on the fact that T from earlier was equal to 2 pi over omega. Now, what you're doing in this is you're subbing in omega. So we have omega here. Omega is equal to V over R. So I'm going to sub in omega. T is equal to 2 pi over omega is V over R. V over R. I'm going to sub that in, which tells you that T is equal to 2 pi R, because you're going to invert this and multiply. So 2 pi R over V. So T is equal to 2 pi R over V. That's equation number 8. And now I'm going to go into the next equation, equation number 9. Actually, I'll write out all 4 of the next equations that you need together. So equation number 9 is x is equal to a sine omega t. Equation number 10 is equal to x is equal to a cos omega t. Equation number 11 is x is equal to a sine omega t plus alpha. Equation number 12 is x is equal to a cos omega t plus alpha. And once again, none of these are in the tables, so you need to know these off by heart. And same goes for this one. And no, this one's in the tables. Okay, so actually I think this one's in the tables, so you can leave out this one. This one's in the tables, but you need to learn this, this, and this. And these two are the most important ones that you need. So I'll explain them now. This equation is used when a particle is coming from the center. So I'll draw the line again. You have the line. In the middle, you have the equilibrium. I'll call this end of the amplitude A, and I'll call this end of the amplitude B. So this. So let's say you have a spring, so a compressed spring. I'll draw that in as well. you have a compressed spring. You have that bouncing up towards the center. So the center is E. So it's opening out and it's coming towards the center. Let's say it's at this point over here. So it extends out so much that it comes out to this point over here. So that's its X position. And when it's coming towards the center, you're going to use, when it's going towards the center, you're going to use A cos. You're going to use this equation over here. This is the equation you use when something is coming from the amplitude. Something's coming from the amplitude to the equilibrium point. AX is equal to A cos omega t. So omega is a constant, so you'd be given that in the question. A is also a constant. A being the amplitude is also a constant. You'd be given that in the question. And then you may be given X or you may be given time. And you can figure out the other one if you know one of them. And so if the object or the spring is going from the extreme point, the extreme position, the amplitude A, towards E, and it's at point X, you use X is equal to A cos omega t. Now, for this one, I'll use a different color for this. So you have X is equal to A sine omega t. This equation is used when a spring is already at this point over here and it's going away from the center. So it may be going in this direction, let's say. It's coming away from the center. So so you have, let's say it goes out to here. So it was at the center and now it's moving away from the center in this direction to the right. And before it was moving from the extreme point to the center, from extreme to center, and now from here it's moving from the center towards the extreme point. Now you use this equation, this one. This one, if you're going from the equilibrium to the extreme point. Now this could be going from E to B or from E to A. You could use it in both cases. Likewise, you can also use this equation if the particle was going from B to E. So that's the difference between equation number 9 and 10. You use equation number 9 when something is going from the center to the extreme point. You use equation number 10 when something is going from the extreme point to the center. Now these two equations, these are a little bit trickier. We will come across them in questions, so that's where I'll explain them. These are basically if something doesn't start at the center or the extreme point. So let's say something starts, a spring starts over here, and is moving towards the center, or it could start anywhere. You could use these two. So watch out for some of my future videos. I will be using these 12 equations in some of the next few videos that I make to show how they're actually used in actual Leaving Cert questions, which often appear in question 6 of the paper. So I'll see you in the next video.